Here we're going to look at the chemistry of carboxylic acids. Carboxylic acids all have this COOH functional group, where you've got this OH group bonded to a carbonyl carbon. An example of a carboxylic acid would be and when writing this down as a structural formula, the carboxylic acid group is written as a COOH in that way. Now, in naming this carboxylic acid, we've got to remember that the carbonyl group, the carbonyl carbon, is always carbon 1. So that makes my longest carbon chain 3, with a methyl group here on carbon number 2, which makes this molecule methyl propanoic acid. So the suffix for carboxylic acid is oic acid. We don't need a 2 in front of the methyl because it can only be on carbon 2. If the methyl was on carbon 3, then that would simply extend the chain and make it butanoic acid. Two structural features of this this carboxylic acid functional group. Firstly is the delta positive carbon, and that's obviously delta positive because it's part of a polar bond where the oxygen is a lot more electronegative, so withdraws the electron density a lot more, making this carbon delta positive. Now, this delta positive carbon means it can be attacked by nucleophiles. And we're going to look at one specific reaction where this carbonyl carbon is attacked by nucleophiles, and that reaction is esterification, and that's going to be looked at separately in a later video. The other structural feature we need to look at is the acidic hydrogen, which means that hydrogen is relatively easily lost, and that's what we're going to look at in the rest of this video, the acidity of these carboxylic acids. So we're going to have a look at two equilibrium processes. The first one is ethanol, and ethanol dissociating, which is a posh word for splitting up, into these, what we call these ethoxide ions, CH3, CH2O-, and hydrogen ions. And we're going to have a look at another equilibrium process, this time ethanoic acid. And ethanoic acid dissociating or splitting up into ethanoate ions and hydrogen ions. Now, this equilibrium is what we call an acid. Is acid dissociation. So the equilibrium constant associated with this is called the Ka acid dissociation constant. And the stronger the acid is, the more dissociation we get, and the larger the Ka. So stronger the acid, the larger the dissociation, therefore the more the equilibrium lies to the right. Therefore the larger the Ka. Okay, so my question would be then, which of those two equilibrium processes would have the largest Ka? which of those is the strongest acid. The strength of the acid, the size of the Ka, depends on the stability of the negative ion formed. Let's have a look at the negative ion formed in the first equilibrium process. So we've got this ethoxide ion. In this ethoxide ion, the negative charge is localised on one atom, the oxygen. Localised means you stay in one place. Now, if we have a look at the negative ion in equilibrium process B, we form this ethanoate ion. But in reality, this negative charge, rather than being localised on this one oxygen, this negative charge can actually spread around over the whole carboxylate group. So you can think of this pair of electrons actually doing something like this. So we see now the negative charge is here. Now in reality, the negative charge is actually spread over the whole carboxylate group, and we can write it down like this. The negative charge is actually spread over this whole carboxylate group. So instead of being a single bond and a double bond, we actually can think of this being 1.5 bonds and this being 1.5 bonds. And because this negative charge is spread over a larger volume, it makes that ion more stable. Hence the Ka is going to be much larger for equilibrium B, because this negative ion is much more stable. Let's have a look at another equilibrium process. I'm going to call this now C. And again, I've got my Ka. So now let's have a look at equilibrium process B and C. Which of those is going to be the highest Ka? Equilibrium process B or equilibrium process C? Well, let's have a look at the negative ion formed in the equilibrium process C. What we've got here now is, instead of 3 hydrogens, I've now got 3 chlorines bonded to a carbon, bonded to the, I'm just going to write this down slightly differently, bonded to the carboxylate ion. Now we can see in this process again, the negative ion is spread over the whole carboxylate group. The difference being now is I've now got 3 chlorines here rather than 3 hydrogens. Now chlorine is what we call a very electron withdrawing group. They withdraw electron density towards themselves. So Cl are what we call electron withdrawing relative to hydrogen. So this helps stabilise the negative charge on the carboxylate even more. So this negative charge, which is spread over this whole region here, is spread even more because these chlorines here are pulling electron density towards themselves, which means that this negative charge is spread even more over the whole molecule, which makes this negative ion more stable, which means the equilibrium is going to lie even further to the right. That there summarises the chemistry of carboxylic acids. Again, we will look at esterification reactions separately in a later video.